Check one. Check one. Recheck one. Recheck two. Right. Good evening, everybody. Now tomorrow is the last session. Today is the last day before session. Okay. Electromagnetism part. Electromagnetism part. Uh, in the seminar, we touched it a little bit. I think in Candy Batch 2 seminar, we couldn't complete it. Those questions are there. Plus, essay questions are also there. Now, newly there is a pattern of asking questions from electromagnetism. Or a pattern in essay questions. So those pattern also will be discussing. So electromagnetism theory part as a revision, MCQs that were left in the final seminar, plus new pattern of essay type questions from electromagnetism. Today we'll be discussing and finishing. The session will be a bit long. Hari, tell me, is all the DOs perfect? Again, this thing is monitor is there. We'll use the group. All okay. YouTube people. Hari, YouTube also okay. Okay, no? Hari, ne? Perfect. Hari, right. Without talking a lot, we'll quickly start because a lot of things are there for us to finish. Electromagnetism. Electromagnetism. Listen. Now, we are going to revise and go and then do the question. Sorry, right? Electromagnetism. Listen. In electromagnetism, there are three important theories. In electromagnetism, three important theories are there. First, we talk about magnetic effect on a current carrying conductor. On a current carrying conductor. On a current carrying conductor. Magnetic effect on a current carrying conductor. Number two, force acting on a current carrying conductor. On a current carrying conductor. On a current carrying conductor. Placed in magnetic field. Placed in magnetic field. Placed in magnetic field. Finally, electromagnetic induction. Finally, electromagnetic induction. Three theories are there. Magnetic effect on a current carrying conductor. Force acting on a current carrying conductor placed in magnetic field. Electromagnetic induction. Right. Simply, What does these theories talks about? What does these theories talks about? Listen, will you? What does these theories talks about? First, magnetic effect. Magnetic effect. What's the effect? Magnetic effect on a current carrying conductor. Current is I. First theory, we talk about the relationship between magnetism and current carrying conductor. Current carrying conductor and magnetism. What's the relationship? M and I. Magnetism and current carrying conductor. What's the relationship? We talk under the first theory. Second theory is the advanced version of first theory. Second theory is the advanced version of first theory. See, in second theory, we talk about the relationship between force, current carrying conductor, current, magnetic field, magnetism. In first theory, only magnetism and current carrying conductor. Second theory, we talk about current carrying conductor, magnetism, additionally about force. First theory, only magnetism, current carrying conductor. Second theory, current carrying conductor, magnetism plus force. Additional something is there. Third theory is the opposite of second theory. Third is the opposite of second. Third is the opposite. Second theory is opposite is third theory. That's it, the three theories. First theory, we talk about the connection between magnetism and current carrying conductor. Second theory, one more additional, magnetism is there, current carrying conductor is there, what's the force acting there? Third theory is the opposite of second theory. Sorry, one by one, we'll go through the theories. One by one, we'll go through the theories. First, magnetic effect on current carrying conductor. First, magnetic effect on current carrying conductor. Magnetic effect on current carrying conductor. Magnetic effect, magnetism, current carrying conductor, current, what's the relationship? Magnetic effect, current carrying conductor, what's the relationship? Listen. What does this first theory tells us? Listen. When there is a conductor carrying some current in it, when there is a conductor carrying current, when there is a conductor carrying current, around the conductor, that means in the vicinity of the conductor, there will be a magnetic field. Around the conductor, there will be a magnetic field. That means, now see, take this wire, will you? Take this wire. Let's take this wire is carrying some current. This wire is carrying some current. When this wire, when this conductor carries current, around this wire, there will be a magnetic field created. When it carries current, around this wire, there will be a magnetic field created. Any wires like that. Now you take your, let's take you are using a laptop. Your laptop charge a wire. Current is going. When current is going, around it, a magnetic field is created. Any wire you take, in your houses you have wires. Any wire, when it carries current around it, you call it in the vicinity of the conductor, around it, there will be a magnetic field. That is what first theory tells us. Tell me, is that part clear? Is that part clear? Is that part clear? Are it clear? Clear? Clear, no? Increase the sound a little bit. Is there issue with the sound level? Is there issue with the sound? No? No. No issue. So remember, what does the first theory tells us? When a conductor carries current, around it, in the vicinity of the conductor, there will be a magnetic field. Okay, that means simply like this. Around a current carrying conductor, magnetic field is created. A current carrying conductor is just like a magnet. See, around a magnet also you have magnetic field. Around a current carrying conductor also you have magnetic field. That means a current carrying conductor is just like a magnet. It's just like a magnet. It's just like a magnet. Sorry. One more point. Can we find the direction of magnetic field? Now here, see, I mark the direction of magnetic field this way. How did I mark it? Can we find the direction of magnetic field? Yes. There are two rules to find the direction of magnetic field here. One, Maxwell's corkscrew rule. Two, right hand grip rule. I recommend you to use right hand grip rule. It's more easier, right hand grip rule. What does right hand grip rule tells us? You take your right hand, you point the thumb in the direction current flow, then all the other four fingers shows the direction of magnetic field. See, thumb direction of current flow, all the other four fingers direction of magnetic field. See, thumb direction of current flow, all the other four fingers direction of magnetic field. That means take this wire value, take this wire value. Hurry, take this wire value, this wire. Let's take there is current flowing in this direction. Current is flowing this way. Then what is the direction of magnetic field? I point the thumb in the direction of current flow. All the other four fingers shows the direction of magnetic field. So this is the direction of magnetic field. This way the magnetic field is going. This way the magnetic field is going. That's the direction. That's the direction. Now, in case if the current flows downwards, then what's the direction? See, thumb is down, all the other four fingers shows the direction of magnetic field. So this is the way. I can't rotate it and show. This is the direction. This is the direction. That's the direction. If current flows down, this way. If current flows up, this way. That is right hand grip rule. Got it? Got it? Got it? Got it? Hurry. 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 Right. Now, is it standard to draw like this and show? This way drawing and showing. Is it standard way to draw like this and show? You can't draw like this. There are symbols to show this. See, current carrying conductor, current is running in that direction. Magnetic field from this side going into the board. From the other side coming out of the board. See, from this side going in, from the other side out. Again, see, from this side in, from the other side out. In is shown by circle and a cross. Circle and a cross in, going into the board. From the other side coming out. Out is shown by circle and a dot. So circle and a dot out. So when I draw these two symbols, now you can see from this side in, from the other side out, this way you have a magnetic field. This is the standard way of representing the magnetic field. See? Current is flowing this direction. Right hand grip rule. From this side in, look at my fingers. From this side in, from the other side out. From this side in, from the other side out. From this side in, circle and a cross. From other side out, circle and a dot. This is out, this is in. That is how you mark the magnetic field. Tell me, is that part clear now? Is that part clear? Sorry? Clear? Use right hand grip rule. That's more easy. More than Maxwell's corkscrew rule. Harid. Harin? Hari? Ah. Now you all try for this thing. Current flow downwards. You all draw in a paper and do it. Huh? You all draw in a paper and do it. From this side into, draw in the paper and check. From this side into the paper or out of the paper. In, no, out. You all do it and see. You all do it and see. Don't worry, I'll give a calendar sheet note. You all know my notes now. I'll give a calendar sheet note. Now first listen and tell me that side in or out. This side in or out. Everyone. Don't do to the board, do to a paper. Do to a paper. Do to a paper. Perfect. Out. Out. Hey, now see. Thumb is going down. From this side out. See? Thumb is going down. From this side out. Out kyanne circle and a dot. From that side out. Then from this side guaranteed in. From this side in. That side in. That side in. Hurry, ne? Ena will write a short note on this. If you can take a calendar sheet. Aravi, calendar sheets notes tamai. Nattang me A4 sheet tag hari monhari. Dingala we are going to write. Main heading electromagnetism. Main heading electromagnetism. Main heading electromagnetism. Under that. Under that. First take the paper. You all took the paper. Can't we use both hands for this? Banning. You use both hands, you will get two different answers. In your paper, write down electromagnetism. 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 Under that, write down number 1, magnetic effect on current carrying conductor. Magnetic effect on current carrying conductor. Magnetic effect on current carrying conductor. In a very short format, we are going to write, right there. When a conductor carries current, when a conductor carries current, when a conductor carries current, there will be a magnetic field. There will be a magnetic field in the vicinity of the conductor. In the vicinity of the conductor. There will be a magnetic field in the vicinity of the conductor. There will be a magnetic field in the vicinity of the conductor. That's it. Now you draw this and draw this. That's it. Right hand grip rule is used. Don't use Maxwell's corkscrew rule. Use right hand grip rule. What is vicinity? Vicinity means around it. Harine. Shall I change? Once when you're fully finished, Lama, I put a photo of the full note to the group. So in case if anyone else has missed the note due to any connection issue, they can get it. Sorry. Har. Now going to the second theory. Now going to the second theory. Now going to the second theory. Second theory is force acting on a current carrying conductor placed in magnetic field. Placed in magnetic field. Now listen, eh? Now listen. Force is acting on a current carrying conductor. Current is there. Placed in magnetic field. Magnetic field is there. Now listen. Lamai, this second theory is a advanced version of first theory. Now, what does the first theory tells us? What does the first theory tells us? When a current carrying conductor, when a conductor carries current, around it magnetic field will be there. When a conductor carries current, around it magnetic field will be there. That is what first theory tells us. When a conductor carries current, around it magnetic field is there. Kiyanne, a current carrying conductor is just like a magnet. Agree with that? A current carrying conductor is just like a magnet. Agree with that? Because around it, you have magnetic field. It is just like a magnet. Agree? All of you all? All of you agree? Mari. So current carrying conductor is just like a magnet. It's just like a magnet. Hari. Now using that, we are going to make a little bit of an advanced theory. We know a current carrying conductor is just like a magnet. A current carrying conductor, listen, eh? A current carrying conductor is just like a magnet. Then instead of drawing this, I will draw a magnet here. A current carrying conductor is just like a magnet. Instead of that, I can draw a magnet there. North pole is there, south pole is there. This is a current carrying conductor. It's just like a magnet. Now think, when this current carrying conductor is placed closer to another magnet. Now this is a real magnet. Another real magnet. This is a current carrying conductor which is like a magnet. This is another real magnet. Listen very carefully. This is a current carrying conductor which is like a magnet. This is a real magnet. Now think. This grade 6 question. Two magnets are there. When they are kept closer, what will happen? It's a grade 6 question. Huh? Two magnets, when they are kept closer, what will happen? Two magnets, when kept closer, what will happen? What a lazy question. Eh? Two conductors kept closer, what is going to happen? Two magnets kept closer, what's going to happen? Marui. It might attract or it might repel. Now here in this instance, of course, it will repel. Which means when two magnets are kept closer, there can be a attraction force. Listen to the words I'm using. There can be a attraction force or there can be a repulsion force. There can be an attraction force or there can be a repulsion force. That means when two magnets are kept closer, guaranteed there will be a force acting. That's it. Second theory. Oh, this is what second theory tells us. When a current carrying conductor, which is already like a magnet, is kept in magnetic field, again another magnet, two magnets are kept closer. What will be acting? A force will be acting. See? When a current carrying conductor, which is just like a magnet, kept closer to another magnet, a force will be acting. Correct? When a current carrying conductor, which is just like a magnet, kept closer to another magnet, between them, there will be a force acting. Attraction or repulsionary force will be acting. That is what second theory telling us. What is a grade 6 theory? Two magnets closer, attraction or repulsion will happen. That is what they are telling. Now tell me, is second theory clear? Now tell me, is second theory clear? I don't keep any doubts. Understand the theory and do it. Two magnets are kept closer, attraction or repulsion will happen. Grade 6 child knows that. Because I teach it to grade 6. Grade 6 child knows that when two magnets are kept closer, there will be attraction or repulsion. Right? Right? I think. So that is what second theory is telling us. Force acting on a current carrying conductor placed in magnetic field. But there is one important point here. The current carrying conductor should be placed perpendicular to the magnetic field. Current carrying conductor should be placed perpendicular to the magnetic field for this force to act. Now tell me, if conductor and magnetic field are parallel, this is the current carrying conductor, this is the magnetic field. If they are parallel, will there be a force acting? If they are parallel, will there be a force acting? No. Only if conductor and the magnetic field are perpendicular again 90 degrees, a force will. That produced force will also be perpendicular to both current and magnetic field. Current is there, current is in this direction. Magnetic field is there, magnetic field should be perpendicular. Then only a force will be generated. That produced force is also going to be perpendicular to both these components. Reduced force is also perpendicular to both those components. Sorry, reduced force is also perpendicular. So if they are kept parallel, will there be a force generated? Nahi beta. Nahi. Only when current is flowing perpendicular to magnetic field, a force will be generated. Only when this instance is completed, a force will be generated. Clear? 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 Hari? Hari? Hari, ne? One more point. One more point. Now let's take direction of current is given. Direction of magnetic field is also given. How to find the direction of force? How to find the direction of force? How to find the direction of force? Don't write anything. At the end, we'll be writing how to find the direction of force. Listen, will you? How to find the direction of force? To find the direction of force, what is the rule you are going to use? You use Fleming's left hand rule. What's the rule you use? Fleming's left hand rule. Fleming's left hand rule. Now, what does Fleming's left does? Okay. Take your left hand. Left hand. Make left hand. Take your left hand. You point your index finger to the direction of magnetic field. Index is magnetic field. Index is magnetic field. Index is magnetic field. You point your middle finger to the direction of current flow. Middle finger current flow. Middle finger current flow. Both should be perpendicular. Then only a force will be generated. Middle finger to the direction of current flow. Then you open your thumb. Thumb points the direction of force. What does Fleming's left hand rule tells us? You take your left hand. You point your index to the direction of magnetic field, middle finger to the direction of current flow. Automatically, your thumb will point the direction of Fleming's left hand. We'll do some questions from this. See, let's take current is flowing to, magnetic field is to this direction. This is the direction of magnetic field. Current flowing out of the board. Circle and a dot. This is the direction of current. Direction of current. Magnetic field this direction, current is this direction. My question, what is the direction of force? Write it in your writing book. Don't do it to the board, because at the end of the day, you should do it to a paper. So do it to a paper. Write it in your writing book. First one I'll do. Index. But only your index. All the other fingers should be closed. Only your index. Index to the direction of magnetic field. Then you point it to that direction. Current is coming out of the board. Current is shown by middle finger. Middle finger is out like this. Index is that direction. Current is this direction. Then when I open the thumb is pointing where? Thumb is pointing where? Thumb is pointing where? Upward, Marui. So what's the direction of force? Force is upward direction. Again, see, how did I do this? Index to the direction of magnetic field. Middle finger to the direction of current flow. Now, some people have a born defect. Once when they open the thumb, okay, thumb in this direction. When they open the middle finger, all the others will open and hand will go to somewhere else. එහෙම වෙන්න බෑ. When you point your index, index is locked to this direction. This can't change. It can't again go anywhere. එහෙම බෑලා. Ballet dance නෙවෙයි. මේක මේ පැත්තට. You can't change. Once you open your middle finger, still this can't change. See, did my index change? Nah, එහෙම බෑ. When you open your thumb, nothing can't change. Nothing can change. All the others should be closed. All the others are closed. This, and here. Hurry. Shall we do for one more? Second one. Now your turn. Magnetic field, this direction is out of the board. Find me the direction of force there. Find me the direction of force. Find me the direction of force. Do it for your writing book and don't do it for the screen. Do it for your writing book. Direction of force. What? Good. See? Magnetic field this direction, index is this direction. Now hereafter you can't change the index. Index that direction, index you can't change. Current is out of the board. Now you need to turn your hand other side. See? You need to turn your hand other side. You turn your hand other side. Now see? Magnetic field that direction. Some people can't turn it. You need to do it. Now you put your thumb this way, down, thumb is down, thumb is down, thumb is down, force is down, force is down. Thumb is down, force down, thumb down. Now do third one. Magnetic field is out of the board. Now magnetic field is out. Magnetic field is out of the board. Current is this direction. Current is that direction. I want you to find the direction of force. Is it A or B? A the B the. Can come for MCQ question. A the B the. 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 Properly do and tell. Now you are not at a rush. Properly do and tell. A the B the. YouTube people also. I'm checking the YouTube chats now. YouTube people also. A the B the. A the B the. A the B the. Perfect. Now do. Magnetic field out of the board. Index is out. Index is out. Now index is only out. Magnetic field is out of the board. Current is flowing upward. Current is flowing upwards. Now open your thumb. Thumb is where? thumb is to this direction, thumb is to that direction. That is force is A. Force is A. Mari? Force is A. So that's how you find the direction of. That's how you find the direction of force. Fleming's left-hand rule. Finally, what are the applications of force acting in a current carrying conductor placed in magnetic field? What are the applications? Only two applications are there. Only two applications are there. What are the two applications? Number one, loudspeaker. Number one, loudspeaker. And number two, direct current motor. Direct current motor. Loudspeaker, direct current motor. Loudspeaker, direct current motor. One more point. What are the factors that affect the force? What are the factors that affect the force? Affecting force. Now we know when a current carrying conductor is placed in magnetic field, a force will be produced. What are the factors that are going to affect the force that is generated? What are the factors that can increase the force? What are the factors that can decrease the force? Listen, will you? Three factors are there. One, amount of current. Of course, yes, no, lamai. When you send a large current, force will be greater. When you send a small current, force will be small. Number two, magnetic field. Number two, magnetic field. When the magnetic field is more, when you use a larger magnet, guaranteed the force is going to be more. Take a big magnet, the force will be more there. Number three, length of the conductor. Number three, length of the conductor. When length of the conductor is more, force will be also. So when any of these factors are increased, force will also increase. When any of these factors are decreased, force will also. HRI. Second theory done. Fully done. Fully done. Again listen. What are the things that second theory telling us? What are the things that second theory telling us? Patta lazy. When a current carrying conductor is placed in magnetic field, what will be generated? Now, these things should come into the mind. When a current carrying conductor is placed in a magnetic field, what is generated? A force is generated. But for this to happen, your current and magnetic field direction should be perpendicular to each other. Then force generated is also perpendicular. Force is also perpendicular. I'll draw it here itself. Force is also perpendicular. Force is also perpendicular. Current is there. Magnetic field is there. They should be perpendicular. Force is also perpendicular. Force is also perpendicular. Next, what is the rule we use to find the direction of force? Fleming's left-hand rule. What are the applications? Loudspeaker, direct current motor. What are the factors affecting the force there? Current, amount of current, magnetic field, the strength of the magnet, and finally, length of the conductor. When any of these factors is increased, force will also increase. HRI. HRI, second law, second rule. Tell me any doubts. Tell me any doubts up to there. Clear? Crystal clear? Crystal clear? හරිනේ. එහෙනම් ළමයි මේ we'll write it in the calendar sheet itself. First write down the heading. Second theory. Force acting in a current carrying conductor placed in magnetic field. Force acting in a current conductor placed in magnetic field. Force acting in a current carrying conductor placed in magnetic field. First write the heading. Force acting in a current carrying conductor placed in magnetic field. Under that, write down, when a current carrying conductor, when a current carrying conductor when a current carrying conductor when a current carrying conductor is placed in a magnetic field is placed in a magnetic field is placed in a magnetic field is placed in a magnetic field, a force will be generated. A force will be generated. A force will be generated. This size, is it visible enough? That size screen, is it visible enough? Can write the nathang, should I make it bigger up to about this size? Visible or not visible? Can? Now everything goes to the calendar sheet. Write the things in the calendar sheet. So this tells the rule. This tells the perpendicular story. This is the left-hand rule. These are the applications. These are the factors affecting the force. 2 minutes. Write it. So is this your last class? No, tomorrow will be the last class. What is the topic for tomorrow? This one's last topic is the transformer section that is kept for tomorrow. I usually finish the class with transformer section. How to find the direction of current? Current flows from positive to negative terminal. Is there recording of yesterday's class? Yes, they are in the YouTube. Plus lamai small thing. We have hit 4K on YouTube just now. Just now we have hit 4K on YouTube. 4K subscribers on YouTube. Thank you. Finish with this. Done. Next year for other batch, if you are doing physics night, will you invite us to sing song and also? Next year batch plan is huge. Right? Already the structure is being constructed. Right? Next year everything is going to be planned. Top to bottom. Everything goes according to a plan. Even and the next year starts for the next year batch. How the physics night is, how the things are going to work. Reveal karanna. But of course, I want your support. Next year, this year's batch support is here now. Last year's batch support was there during this year. Next year, a huge support is needed from your end. First, finish your O level, passe, ඒව ටික අපි plan කරගමු. Stay in the groups and don't leave the groups. හරිද මේ? ඒ කියන්නේ we'll use the group in an official manner. හරිද? එහෙම use කරමු මේ if there are any unnecessary people ඒව ටික we'll remove and go. And then make the groups clean. After the groups are fully cleaned, after that we'll use it for a good purpose. Hari. During your A-levels journey also, you can use the groups. May you get doubt clearing or what groups you can use. I will open the groups and key. So once when few people start messaging unnecessarily, we'll remove, reset the link. It's a constant group. So all the 4 groups are constant groups. Only for the betterment. And plans, I will tell you all. I want your support also next year. Because I am not a teacher who is connected with so many other teachers. No, whatever I do, I'll have to do alone. When doing alone, maximum support is needed from the students. That's how things can work out. So next year, I want your support. However, physics night again, I'll tell you. Until O level only, I am your teacher. After O level, all are my brothers and sisters. Even last year, I just like that we go out, we eat. Trips 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 එකක් වගේ ගියා. එකක් වගේ ගියා. හරි. Father son නෙවෙයි. I am not your father. I am 21. Brother, sister. එහෙම young. Father son එපා. හරි. Next one, last one. Electromagnetism. Sorry, electromagnetic induction. Electromagnetic electromagnetic induction. Hurry. Listen, will you? Electromagnetic induction is opposite of the second theory. Electromagnetic induction is the opposite of second theory. Now, what does the second theory tells us? Second theory tells us when When a second theory, and this second theory tells us when a current carrying conductor is placed in a magnetic field, what is produced? Force is produced. That is second theory. Induction is the opposite of this. Now your turn. Induction is the opposite of it. Now your turn. When a force is given to a conductor placed in magnetic field is also there. Think and tell me, what should be produced there? What should be produced? What should be produced? What should be produced? Think and tell more. Practically think and tell. What should be produced? Anna hurry. Current should be produced. Current should be generated. Current should be generated. That is what induction tells us. When a force is given to a conductor placed in magnetic field, current will be generated. Actually speaking, directly the current won't be generated. What is generated there is a EMF, electromotive force. When an electromotive force is generated, it's like voltage, Fleming. When a voltage is created, guaranteed a current flow will be there. So what does electromagnetic induction tells us? When a force is given to a conductor placed in magnetic field, an electromotive force will be generated. When a force is given to a conductor placed in magnetic field, an electromotive force will be generated. That is what third theory tells. Tell me, is that part clear? Tell me, is that part clear? Is that part clear? Hurry. 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 Force is given to a conductor placed in magnetic field, a EMF, electromotive force will be generated. When a force is given, when a conductor placed in magnetic field, EMF will be generated. Electromotive force will be generated. But here also we have some rules. Number one, the force should be perpendicular to the magnetic field. The force should be perpendicular to the magnetic field. Force and magnetic field should be perpendicular. The current will be produced. Produced current is also going to be perpendicular to both the other factors. Force, magnetic field should be perpendicular, then a current is produced. Produced current is also perpendicular to both of them. So all these three factors are going to be perpendicular. All these factors are perpendicular. Next. Now listen. Next. Now what you're actually doing is, magnetic field is down. Now this is a magnet. Magnetic field is down. In magnetic field, you keep a conductor. In magnetic field, you keep a conductor. And you're giving a force. When the force is given, conductor will move, isn't it? Think practically. When let's take I supply a force in this direction, guarantee the conductor is going to move. There will be a motion in the conductor. There will be a motion in the conductor. Remember, the motion of the conductor should be a relative motion to the magnetic field. Relative to the magnet, the conductor should show some movement. Relative to the magnet, the conductor should show some movement. Let's take, this is the magnet. Listen very carefully. This is the magnet. This is the conductor. I am moving the conductor like this. See, relative to the magnet, conductor is showing some movement. If I move both of them like this, tell me, relative to the magnet is conductor showing any movement? Both are going like this. Both are going. Relative to the magnet is conductor showing any movement. Relative to the magnet is conductor showing any movement. Tell me. Something to think there. If I move both of them like this, relative to the magnet is conductor showing any movement. Nanny. See? Relative to the magnet, conductor doesn't show any movement. Nanny. Then will there be a current produced? Now look at this. Relative to the magnet, conductor is showing some movement. Relative to the magnet, there is a movement. This has a movement. This, is it having a movement? No. Now if both of them are stationary, is there a movement? No. So unless there is a movement, unless there is a relative motion, there won't be a current produced. For the current to be produced, there should be a relative motion. No relative motion, no. Hurry. Got that point? Got that point? Got that point? Hurry. So remember, relative to the magnet, there should be a motion, which means there should be a relative motion. There should be a relative motion. Unless there is a relative motion, there won't be a current produced. This is a more important part. Huh? Again listen, again listen, again listen, again listen. See? Again listen. Again listen. Again listen. This is the magnet. This is the conductor. If both are moving together, if both are moving together, if both magnet and the marker pen are moving together, relative to the magnet, is the conductor showing any motion? No. There is no relative motion there. Relative to one another, there is no any motion. But now, there is a relative motion. Relative to one, the other is moving. Relative to one, the other is moving. This is a relative motion. There should be a relative motion for this current to be produced. Tell me, the ones who couldn't understand in the first shot, now clear? Yes, 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 yes. All right. So there should be a relative motion. Next, what is the rule we use? What is the rule we use to find direction of current? Fleming's right hand rule. Now right hand comes. Fleming's right hand rule. What does Fleming's right hand rule tells us? You take your right eating hand, right hand. You point your index in the direction of magnetic field. Always index is magnetic field. Index in the direction of magnetic field. Thumb in the direction of force. Then your middle finger will show the direction of current. Index magnetic. Thumb force. Middle direction of current. You take your right hand. You take your right hand. Take your right hand. You point your index in the direction of thumb in the direction of force. Automatically, middle will show the direction of middle shows the direction. If I draw it and show, see, magnetic field this direction. Magnetic field this direction. Force is upward. Force is upward. Current out of the board into the board. Think. Magnetic field this direction, force is upward, current is out or in. Do with me. See. You take your right hand, index finger direction of magnetic field, index direction of magnetic field. Thumb shows the direction of force. Automatically, middle will show the direction of current. Can you see middle finger is out of the board there? Middle finger is out of the board there. Middle finger out of the board now. Current flow is out of the board. Current is out of the board. Second one, your turn. I want the direction of current. I want the direction of current. Everyone do. Everyone do and find the direction of current. Everyone do it and find the direction of current. Perfect. Perfect. See, your right hand is what you should be careful. Your right hand. Index magnetic field. Which direction? Index is that direction. A thumb force. Force is down, you turn it down. Force is down, you turn it down. Now open your middle finger. You can't see it from your end, but I can see. Middle finger is going into the board. Middle finger into the board. Into the circle. The direction of current. Middle finger into the board. Circle and across. Circle and across. Into the board. Third one you all do. Force is that direction. Magnetic field is that direction. I want you to find the direction of current. Up the down. Up. Down. Up or down. Tell me. Up or down. Up or down. Everyone. Up or down. Perfect. See. See now different. Right hand. First magnetic field. Magnetic field is index finger out of the boot. Then magnetic field this direction. Magnetic field that direction. Right. Magnetic field that direction. Force is that way. Then thumb that direction. Correct? Thumb that direction. See? Magnetic field out. Thumb that direction. When I open my middle finger is down. See? Middle finger is down. Middle finger is down. Current is which direction? Current is which direction? Downwards direction. That's the direction of current. Again, see? Your right hand in out of the board. Thumb this direction. Correct? Thumb that direction. See? Thumb that direction. Thumb is that direction. Then your middle finger down. Current is down. Current is down. Hurry. Hurry. හරිනේ. Finally, what are the applications? What are the applications? What are the applications? My induction is used in alternating current dynamo, alternating current dynamo, used in bicycle dynamo, used in bicycle dynamo, of course used in moving coil microphone, of course used in moving coil microphone, finally it is used in, there you go, transformers. Transformer. Then what are the applications of electromagnetic induction? Alternating current dynamo, bicycle dynamo, moving coil microphone, transform. Sorry. Finally, how to increase the amount of current? How to increase the amount of current? What are the factors that affect the current produced? How to increase or decrease? Both. What are the factors that affect the amount of current produced? Factors affecting amount of current. Factors affecting amount of current. What are the factors that are going to affect the amount of current? Listen. First one, you are moving the conductor or the magnetic field. No, you are moving it. That means they will have a certain speed. Speed of the motion. Speed of the motion. Speed of motion. ඒ කියන්නේ. ඒ කියන්නේ. ඒ කියන්නේ. Conductor. Magnet conductor. I move it slowly. Current produced is less. I move it fast. Current produced is more. See, magnet conductor, I move it slowly, current is less. I move it faster, current is more. Speed of motion. When speed increases, current will also increase. When speed increases, current also increases. Second one, strength of magnetic field. The magnetic field. Strength of the magnetic field. When magnetic field strength is more, current is also more. That means you use a stronger magnet, current is more. You use a weaker magnet, current is less. Next, of course, length of the conductor, even you can call it number of turns in the coil. Because usually this is used now in all these things. We are using it in terms of number of coils there, in terms of coils there. So if you take a coil, when number of turns in a coil is more, when number of turns in the coil is more, length of the conductor is more. When number of turns are less, length is less. No? So number of turns in the coil, even you can call it no problem. Length of conductor. Length of conductor. That's the number of turns in the coil. Say both are same. When this increases, current is also increased. When it is increased, current is also increased. So what are the factors affecting the amount of current? Speed of motion, magnetic field, length of the conductor. Instead of length of conductor, you can even write number of turns in the coil. You can even write number of turns in the coil. When that increases, current will also increase. That decreases, current will also. These are the factors. I think everything in one calendar sheet. Everything in one calendar sheet. Any doubts there? Any doubts? Any doubts? No? හරි. හරිනේ. Write down electromagnetic induction. First, I will give a sentence and then only we are going to write this. First, write electromagnetic induction. Electromagnetic induction. Under that, write down. Under that, write down. When a force is given, when a force is given, when a force is given, when a force is given to a conductor placed in magnetic field, conductor placed in magnetic field, to a conductor placed in magnetic field, to a conductor placed in magnetic field, to a conductor placed in magnetic field. A electromotive force, a electromotive force, a electromotive force, a electromotive force, brackets EMF, brackets EMF, brackets EMF is induced, is induced, induced, is induced, is induced. Under that draw. Induced means produced. Done. හරිනේ. හරිනේ. Right. Now we'll do some questions. Only transformer part is remaining. That is for tomorrow. Yeah, I told you I finished my session, night session with transformer section. Only transformers are remaining. Hari, that is for tomorrow. And now we'll do some questions. Maybe these days, new syllabus papers, a different type of questions are coming. I saw that question in last year's paper. Same type of question came in this year's support seminar paper also. Electromagnetism part. Last year O-level paper as well as this year support seminar paper. Again, or electromagnetism pattern is a bit changed. But now we can tell the pattern also. එහෙම question එකක් can come for your exam also. මං කියන්නේ අනිවාර්යෙන් එයි කියලා. Can come for your exam also. Sorry, we'll do that type of question first. We'll first do last year's past paper. Last year's past paper question. I didn't put it in the group. Now we are going to do here, right? Now we are going to do. This is last year's past paper, 2022-23 O level past paper. Make a support seminar. Make a support seminar. Hurry, support seminar will finish. This is this year's support seminar. This is this year's support seminar. 2023-24 support seminar. This is not a past paper. This is this year support seminar paper question. Support seminar paper question. Hurry. First go through the question. First go through the question. If anyone has the support seminar paper, put it to the group. If anyone has the support seminar paper, put it to the group. We all can solve it together. Yeah, not clear. Tama iti mata tere. Group. Support seminar paper එක දාන්න ළමයි. Hurry. I'll pass it to the other groups also. Or another one group that's not there. Right. Now look at the question. Look at the question. The last question. A and B conductors are placed on a magnetic field after placing them on a smooth metal rod, as they can move freely on those smooth metal rods. X and Y ends of the metal rods are connected to a transformer. Look at the picture there. Look at the picture. See. AB is a conductor, it seems. AB is a conductor. It's placed in magnetic field. It's placed in magnetic field. First of all, tell me, magnetic field is out the in. Magnetic field is out or in? First of all, tell me, magnetic field is out of the board or in? Sorry, out of the board. I circle and dot. So magnetic field is out. Conductor is placed like this. A transformer is connected. A bulb is given. A bulb is given. Sorry. Now, what are they telling? What are they telling? A and B, sorry, A and B conductors are placed on magnetic field after placing them on a smooth metal rod, as they can move freely on those smooth metals. So they can be moved. That means you can give a force to them. X and Y ends of the metal rod are connected to the transformer. Roman 1. When AB conductor moves from Q to P in uniform speed, from Q to P, this is Q, this is P, this direction it is moving. This is Q, this is P, this direction the conductor is moving. Now think, that is the direction conductor is moving now. That is the direction of force applied need. That is the direction of force applied need. Force is applied this direction, magnetic field is out of the boot. Force is applied this direction, magnetic field is out of the boot. Can't you find the direction of current flow? Tell me. Can't you find the direction of current flow? Quickly tell me. Can't you find the direction of current flow? Force is that direction, magnetic field is out. Can't you find the direction of current flow? Can. What is the rule you are going to use? Force is there, magnetic field is there, current you are trying to find. Right hand, the left hand. The Fleming's right hand, the left hand. What's the rule? Fleming's right hand or left hand? Fleming's right hand or left hand? Right or left? Think. Think. Force is given, magnetic field is there. Current will act. This is electromagnetic induction need. Force is there, magnetic field is there, current will act. Force is there, magnetic field is there, current will act. Force is there, magnetic field is there, force there, magnetic field is there, current will act. What is the rule we use? Right hand rule. Fleming's right hand rule. Fleming's right hand rule. So use Fleming's right hand rule there. Hurry. Now go to the question. Go to the question. What are they telling? When AB conductor moves from Q to P uniform speed, write an observation that can be seen. What you can see as the observation. See, when you move it, current will be produced. When current is produced, what will happen to the bulb there? Bulb will light up. See, when current is produced here, from the transformer voltage will increase, bulb will light up. Then what's the observation? Bulb lights up. Bulb lights up. Sorry, question B. Write the current flowing direction across the primary coil of the transformer with the aid of X and Y. Right. We need to find the direction of current flow. Try to find the direction of current flow. Now try to find the direction of current flow. AB rod is moving this direction, force is that direction. Magnetic field is out. Fleming's right hand rule. Apply Fleming's right hand rule and tell me current is flowing x to y the y to x the current is flowing x to y ඒකත් ඕන්න එහෙම ඕන්න මෙහෙම කියන්නකො ළමයි මෙහෙම කියන්නකො force is this direction magnetic field is out of the board tell me current is up or down current is up or down ඒක කියන්නකො x to y ඕන්න current is up or down now we all work current is up or down right hand rule current is up or down but then take your right hand make a force මේ මොනවද ලියලා තියෙන්නේ අයියෝ this force sorry force take your right hand magnetic field is out of the board magnetic field is out of the board force is this direction force is this direction same type of question we did force is that direction then when you open your middle finger is down middle finger down now current is going to go down current is going to go down now this is the direction that the current is going to flow that's the direction that the current is going to flow if you make a mistake only yo magnetic field this direction force is this way neda force is that force is this direction of force current is up hondai you are correct current is up magnetic field this direction force is this way now current is up current is up when current goes up it goes there current goes there goes to x and then to y comes there goes there so from x to y current is flowing so what's the direction of current flow through y what's the direction of current flow through x and y x to y x to y is the direction of current flow x to y is the direction of current. Sorry. C part. What is the law applied to find the direction of current flow? What's the law you use to define the direction of current flow? Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. Roman 2. Number of turns in the primary coil is 100 while the number of turns in the secondary coil is 1200. 0.25 voltage potential difference takes place between x and y in this activity. Find the potential difference of the two ends of the bulb. Name an instrument which uses may A part take a now don't do because tomorrow we'll be doing transformer section. Once then tomorrow's transformer section is over, again we'll come back to this one and do A part. Do B part. Name an instrument which uses electromagnetic induction effectively. Electromagnetic induction is used in what instrument? Induction happens in what instrument? Induction happens in, moving coil microphone, AC motor, moving coil microphone, AC motor. Those are the answers. Finally, positive and negative potentials are given to X and Y terminal respectively after removing the transformer. Proceed. Transformer is removed. This is AB rod. This is X and Y. To X and Y, positive and negative terminals are connected, it seems. Transformer is removed. No change to the magnetic field. Magnetic field is out of the board. See, positive and negative potentials are given to X and Y. Positive to X, negative to Y. After the transformer. First of all, tell me when it is connected like this. What is the direction of current flow? Positive to negative current will flow. Positive to negative current will flow. This is the direction of current flow. Need. This is the direction of current flow. Need. Agree with that direction of current flow? Agree with that? Agree with the direction of current flow? Positive to negative. That's the direction of current flow. That's the direction of current flow. Sorry? Right. Now what are they asking? Write the direction of motion of the rod with the aid of P and Q. This is P, this is Q. Now tell me, a current carrying conductor, current is there, placed in magnetic field. Magnetic field is there. What is going to be generated? Current carrying conductor is placed in magnetic field. Now what is going to be generated? Now the opposite. Current carrying conductor is placed in magnetic field. What will be generated? Perfect. Force will be generated. How to find the direction of force? Now what rule? Now what's the rule you are going to use? Before right hand. Now what's the rule? Perfect. Left hand. Fleming's left hand rule. Fleming's left hand rule. So they're asking the direction of motion of the rod with A to P and Q. Which direction will the rod move? Rod will move in the direction of the force. Find the direction of force. Is it P or Q? Find it. Current is flowing down. Current is flowing down like this. Magnetic field is out of the board. Find me the direction of force. Is it P or Q? I'll write it in a new space neither. Current is flowing down. Magnetic field is out. Is the force going to be P direction or is the force going to be Q direction? Option is yours. Use Fleming's left hand. Fleming's left hand. What's the direction? Left hand. Magnetic field is out of the board. Magnetic field out. Force is down. Sorry. Current is downwards. Current is downwards. Current downwards now. When I open my thumb is pointing towards what direction? P. See? Magnetic field out of the board. Current is down. I open the thumb is that direction. Then thumb is to P. Thumb is to P. Force is to P. Thumb is to P. A force is to P. Thumb is to P. Thumb to P. Force to P. Then this will be moving in this direction. That is what direction? P. Motion of the rod with A to P and Q. So we can write Q to P. Q to P. That's the direction. Q to P is the direction of motion there. Q to P. Q to P. B. Write an instant usage of this phenomenon. Tell me. Force acting in a current carrying conductor placed in magnetic field. What's the instance of use? Force acting in a current carrying conductor placed in magnetic field. What's the use? What's the use? Yes. DC motor loudspeaker. DC motor. There you go. Loudspeaker. DC motor loudspeaker. DC motor loudspeaker. Hurry. Got it? Once when you see the diagram, you might think like, world's hardest question is there. I can't do this. එහෙමයි හිතෙන්නේ නිකන් look at the diagram will you? මාර upset diagram නේද? Look at the diagram there. When you look at the diagram, you get faintish. එහෙමයි diagrams are given. එහෙමයි diagrams are given. See, diagram එක දැක්කම නිකන් අයියෝ තඩ්ඩි question is there. I can't answer this. එහෙමයි නිකන් we think. Don't judge a book by its cover. Big diagrams will be given. Big charts will be given. Big tables will be given. Big numbers will be given. Happy? When you go inside the question is patta simple. More simple question. Just by looking at the diagram, don't get scared. Hari diagram is given because diagram should be given. ඒකයි diagram is given. ඒව දැකලා බය වෙන්න එපා. අද පාතට බයපඩ වෙන. Big diagrams will be given. But question inside it is patta simple. Any doubts from this question? Now, Samanya, now this is a selection question. Most of you all don't select it after looking at the diagram. හැබැයි ඉතින් මේක select කරේ නැත්තම් පාඩුයි. හරිනේ. එහෙනම් now we all do this question. I will time it and give to you all. I will time it and give to you all. මේකද නෑ නෑනේ last year's paper 22 one. හරි this one. නෑ මේකත් නෑ. This one. Can you all see this? This is 2021 O-level science paper. No. Can somebody put the paper to the group? 2021 O-level science paper. Me. මට මාර සීන් එකක් නේ. My laptop charger in my house, in my home, I'm at Candy. Last Sunday I came, still I'm at Candy. Lap is off. Without the lap, I'm doing it using the desktop here. Starting the meeting from phone. එහෙමයි වැඩේ යන්නේ. So all those papers and the tutes are not there. ඒකයි me directly I downloaded the paper and I'm doing the questions. Until I go there, no charger for the lap. Paper came. I'll forward the paper to other groups. Do question number 8B there. Question 8B. I'll give about 5 minutes. What the section that you can do and finish will? 8B. The share a clear paper. ඒකයි ළමයි මේ this is the paper I got from the internet here. I shared a paper in the group. Use that paper. You all try to do it. Meanwhile, I'll try to get a clear paper. You all use the paper in the group. I'll try to get a clear paper. All right. Here we have a good page. Yeah, this clear. Work. Hurry. Hurry. In figure 1. In figure 1, A, B, and C, D indicate two metal rails. First, analyze it. A, B, and C, D are two metal rails, it seems. Are the same type of question on. Support this year support seminar paper. This is 2021 neither. 2021 O-level paper. Right? Right. PQ is a PQ is a conductor rod which can be slide on the two rails. Right. This is the rod. It can slide, it seems. It can slide. The resistance of the rails and the rod are negligibly small. That means very small resistance. A uniform magnetic field is applied into the plane perpendicular to it on which the metal rails are placed. Now, magnetic field is where? Before, magnetic field was out of the boot. Now, magnetic field is going into the boot. Magnetic field is into the boot. This is magnetic field. It's into the board. Magnetic field is in. Sorry. To it on which metal rails are placed. When the rod PQ is moved to right, towards right, we are moving rod PQ, and electric current is induced in it. Lamai, when you are moving rod to this direction, there will be a force acting there. So force is towards that direction. Force is there towards that direction. Force is towards this direction. Force is towards that direction. Magnetic field is into the board. Force is there, magnetic field is there. What will be produced? Force is there, magnetic field is there. What will be produced? Current will be produced. Force is there, magnetic field is there, current will be produced. Current is going to be produced. How to find the direction of current? What rule you are going to use? Force is there, magnetic field is there, current. How to find the direction of current? What rule? What rule you are going to use? Right, the left? Right. Always remember, right comes second. Induction is second. Here, induction is happening. Induction wallet a right hand rule. Induction wallet a right hand rule. So here, right hand rule can be used. Induction wallet a Fleming's right hand rule. The previous one is the force acting in current carrying conductor kept in magnetic field. Ekat tamai left hand rule. For induction, right hand rule. So induction is happening here, right hand rule. All right. Now with that, we can get into the question. Right. Name the rule which can be used to decide the direction of induced current. Place in elamai. What is the rule used there? Fleming's right hand rule. Fleming's right hand rule. I'll only write right, but you all write fully. Means right hand rule. You can score Fleming's right hand rule. Next. According to the rule stated in 1, does the current flow P to Q or Q to P? P to Q, the Q to P. Now, where is P and where are? This is P, top is P, this is Q. What is the direction of current flow? P to Q, the Q to P. Hurry. Apply the rule and find out. Apply the rule and find. P is on top, Q is on bottom, P to Q, the Q to P. Fleming's right hand. Take your right hand, eating hand, right hand. Magnetic field is into the board. Magnetic field in. Magnetic field is in. Force is this direction. Force is this direction. Then what is the direction of current flow? What's the direction of current flow? Q2. What's the direction of current flow? Q2. Second, magnetic field is into the board. Force is this direction. Force is there. Current flow is upward. Current flow upward. Current is upward. QP. Current is Q2. Current Q2. So that is Q to P. Q to P. Q to P. Next. Due to the induced current QP, due to the induced current in QP, only one LED labeled Y and W lights. Hurry. Now listen, will ekana electronics part is there. Electronics part is there. Now see. Now see. Current will flow from Q to P. This is the direction of current flow. That's the direction of current flow. That current will go to this side and this side. එහෙම නේද? මෙහෙම නිකන් current එක ගිහිලා it goes both the side. Okay? මෙහෙම නිකන් current will goes to both the sides. That's how the current is going to flow. Think practically. Think practically. See, current goes this direction and goes in both the sides. So if I draw, it goes up, goes this side, as well as goes this side. Now think. If I take this side, current goes through this LED, current is going downwards. There is electronics part here. If the LED's arrow direction and current flowing direction are same, LED's arrow is pointing down, current is also going down, then LED will light up. LED arrow direction and current flow direction are same, now it will light up. This side current is coming this way. LED arrow direction, current flowing arrow direction are opposite. It won't light up. It's an electronic part. Huh? So here Y will light up, W won't light up. Y will light up, W won't light up. LED arrow direction, current direction same, now it will light up. If it is not same, it won't light up. So Y will light up, W won't light up. So what is the LED that lights up? Y will light up, W won't light up. Y lights up, W won't light up. State the reason why other LED does not light. This is fully electronics. This is fully electronics. No need to answer that. That is because reverse biased. Reverse biased. Reverse biased. Hurry. Roman 4. Figure 2 shows how a battery and a switch are connected between A and C after removing the two LED. Now the opposite. Now you can understand the pattern of the question also. See, now they have removed the LED and they have connected a battery and a switch. That means now can you understand here current is given. Current is given. Magnetic field is however down. Then you all tell me what is going to be produced. Current is given, magnetic field is there, what will be produced? Now the reverse one. What will be produced? Current is given, magnetic field is there, what will be produced? Unhurry, force will be produced. If the force is this direction, rod moves that direction. If the force is this direction, rod moves that direction. Now what's the rule you use? Before right hand, now unhurry, left hand. Now you can use left hand rule. There you go. State an observation made when the switch in the circuit is closed. Think when the switch is closed. When the switch is closed. When the switch is closed. Where? When the switch is closed. Guaranteed current will flow. This is positive, this is negative. Positive to negative, current will flow. Positive to negative, current will flow. So current goes in this direction, current goes there. Current goes there. And through PQ, current goes downward. Through PQ, current goes downward. Through PQ, current is down. Magnetic field is, current is down. Magnetic field in, current is down. Magnetic field in, current is down. Magnetic field is in, current is down. Now we all tell me what's the direction of force. Apply Fleming's left hand rule. Find me the direction of force. Yeah, right the left the කියලා තහන්න බෑනේ. මේ අර PQ කියලා මහමුකෝ. P the Q the. Now easy to answer. P the Q. P the Q. P the Q. Acceleration. Hmm? Left hand, you take your left hand. Magnetic field is in. Magnetic field in. Magnetic field is in. Current is flowing down. Current is flowing down. Magnetic field in, current is down. Magnetic field in, current is down. When you open your thumb is this direction. Magnetic field in, current is down, then force is that direction. Force is that direction, that is Q. Force is that, and that is Q. So force is this direction, that is Q. So the rod will move in this direction. You can write to Q direction. That's what they previously know, not to Q. Towards this direction. What are they asking? Are they asking a direction? State an observation made when the switch is on. You can write the rod will move. Rod will move. Natta rod will move to right. Rod will move to right. Rod will move to right. Rod moves to right. So right. Next. Name a device made by using phenomenon associated with observation mentioned in Roman 4a. What is this first of all? What is this? This is force acting in a current carrying conductor placed in magnetic field. What's the device? What's the device? Perfect. Loudspeaker and DC motor. Loudspeaker DC. Any doubts? Electromagnetism. Until transformer, everything is done. By tomorrow, transformer is also over. Marasi. Any doubts? Any doubts? All clear? All clear? Diagrams will be big. Pictures will be big. Everything will be big there. A question is what a symbol. Simple and direct. Clear, no? Clear, no? Hari? Clear. Anivarying a section that you can select. Anivarying section that you can select. Hari ennalame. 1 week is there. 1 week is there. Hari. 1 week is there. Don't get panicked at all. Don't get panicked at all. I told you to prioritize and work. That's why even today when I posted the link, I told you. Already I told you. Only those who wanted to cover electromagnetism, electromagnetic induction, join කියලා. Because now numbers doesn't matter to me. ඒක වැඩක් නැහැ. මට ඕනි මේ ඔයාලගේ your timing you should perfectly this thing. හරිද මේ end කියලා එහෙම අරගෙන මේ if you already know about electromagnetism there is no point. This 2 hours you can use it to something else. ඒකයි I already posted only those who want join කියලා. හරි. In the me only those who want I think joined and those who joined clear. Those who joined clear. එහෙම කවුරු හරි බලන්නේ නැත්නම් YouTube එකේ තියෙනවනේ skip කරලා බලන්න. In the prioritize your work, use the time very efficiently. Use the time very efficiently. හරි හෙට දැන් transformer section එක ඒක කරලා තිබ්බනම් එන්න ඕනේ නැහැ ළමයි. අර last day එකට කියලා ආවට කමක් නැහැ. last day නාල වන්දද ප්‍රශ්න නැහැ. හැබැයි ඉතින් if you are done transformer එහෙම කියලා එන්න ඕනේ නැහැ. හරිද? Prioritize and work. If you have to cover something, first give priority to that. A sections ටික cover කරන්න. Before going to bed tonight, have the plan of tomorrow. I yesterday also told the same story. Today work with a plan. Today, this time, you should have a plan. You should have done the plan. එහෙම නැත්තම් you will have a regret inside you. ඔය regret තියාගන්න එපා ළමයි in life. Don't keep regrets in your life. You have a plan, stick to that plan, you do that plan. Obey yourself. Be disciplined to yourself. Listen to yourself. Have sets of rules to yourself. ඒ rules ටික අනිවාර්යෙන් follow කරන්න ළමයි. කண்டிපා அந்த rules follow பண்ணுங்க. Don't go off the track. Surely follow those rules. Surely follow those rules. Have rules. Have planners. Prioritize the work. එහෙම වැඩ කරන්න ළමයි. Don't just keep working without a proper plan. Before tomorrow starts, before you go to bed tonight, have the plan of a tomorrow. What are you going to do in the morning? What are the sections you are going to cover? What are the sections you are not covered? What you are going to prioritize? What paper you are going to... ඒ plan එක හදාගන්න ළමයි. ඒ plan එක අනිවාර්යෙන් හෙට කරන්න. கண்டிப்பா அந்த செக்ஷனை செய்யுங்க. அந்த அந்த பிளானை கண்டிப்பா செய்யுங்க. Without that, don't go to bed. 7 days are there. Any result can be changed upside down. Still, I tell with the responsibility. Still it's under control. It's under your control. The decision is yours. In 1 second, you can take the decision and change yourself completely. That decision is yours. Whether you are going to change yourself completely, fight for the best result that you can, or go with the same flow there. එහෙමම ගිහිල්ලා එහෙමම ඉවර කරනවා. ඕකේ වැඩක් නැහැ නේ ළමයි. ඉවර කරනවා නම් දිනලම ඉවර කරන්න. ஜெயிச்சிட்டு மட்டுமே தான் இதை முடிக்கிறது. இல்லாம முடிக்கிறது இல்ல. Don't focus on anything else, any unnecessary problem, anything that comes. Now don't go to answer. Keep your mind calm and quiet. Every problem will hit you. Now don't go to take answers. Don't go to find solution. Let those problems be. Later you can solve the problem. Now focus on yourself, your studies. Ekada prioritize then. Don't give priority to anything else. Only prioritize your studies. HRI. Don't give priority to anything else. Anything else, anyone else, don't give priority. Only your studies. Studies comes first. Keep on working. Keep on working. Don't unnecessarily waste time on thinking. Don't unnecessarily waste time just by opening the book and dreaming. ඒව ටික control එකේ තියාගන්න ළමයි. When you open the book, yes, dreams will come. You will go off the thoughts. Happy. Bring back your thoughts. Bring back to the flow. Go with the flow. Don't lose the flow. Go in the track. Go in the track. Already you are going in the track. Don't even think of losing the track. Don't even think of giving up this. Until the end line you have come, victory is just in another 7 days. This 7 days, run your best. However, the way you ran this much of time doesn't matter. Now the last few meters, run it in the best way you can. Best way you can. I know you are down. I know energy is down. You are stressed. You are depressed. Happy, push yourself. Happy, go for that victory line. Hari? Hari Hena. Almost 10 minutes for the next day. From today morning, I'm with the same dress. Morning, I had a school seminar. 8 o'clock, from 8 to this time, I'm with the same dress. Hari, now with tomorrow, we'll finish off our sessions. Tomorrow will be your last online day. Hari, after that, might be after the exam, we can take online something. එහෙම නිකන් කතා කරලා discuss කරලා යන්න පුළුවන්. එහෙනම් electromagnetism section is over. Y'all tell me, what do you feel about electromagnetism now? Tell me, what do you feel? What do you feel? What do you feel? There you go. Letter by letter. Letter by letter. P. Next. A. Next. T. E. Next letter. T. Next. A. Next. E. Next. A. Last two. S. Last letter. Y. Part easy. Don't forget the hashtag and the signature. With that, it's King's Perori signing off.